Um, hello, hello everyone. My name is Joan Ejeta, and I'm one of the student executives for the USACM student chapter. And welcome to the final round of the poster competition, where we're having it via Zoom. It's gonna be like approximately an hour and 15 minutes. Hopefully, we're able to stick to time. And I just wanted to give a brief overview of the agenda, where I'll just give a slight introduction about the USACM student chapter, what we do, and also this is the order in which the presenters will be presenting their posters. We have 10 finalists out of a pool of we had about 22 submissions. And then we'll have at the end of the poster presentation, we would have a Google form where we would have the People's Choice Award. The presentation format is basically just a 5 minutes is expected for each presenter where they're meant to present their research. And within that 5 minutes, if you're when it's about 1 minute left, you receive a notification. An emoji would pop up in the screen telling you that you have 1 minute left. And afterwards, we're 2 minutes for question and answers from the audience or the judges that are available at the moment. And please keep to time so we can wrap up on time because I understand it's a Saturday and everyone has things to do as well. The awards are as shown on the screen. We have from first place, where we have travel award to the next US and CCM conference, a trophy and $100 gift card. Second place, the same trophy and $100 gift card, and third place trophy, $100 and $100 gift card. The People's Choice Award will be voted by people that are present here, the audience that are present here. And the judging criteria really is just research about the research objective, the methods, results, how you've posted the visualization effect of your poster, and your communication of your research. Before we start the presentation, just wanted to highlight why, if you haven't joined the USACM yet, why you should join. The advantages of joining, it's like more of professional development. It's an avenue of networking with peers or colleagues or even experts in your field, and also an opportunity to present your work, be in the leadership team. And there are various ways in which you can connect, where we have the LinkedIn, the Instagram, and also YouTube, where we have past videos from different seminars and webinars we've organized in the past. And the pictures on the slide just shows like the various activities that has been done in different local chapters. I think this is a University of Berkeley event that organized last year. With that, I'd like to say each presenter please have your screen, your poster in your screen ready to be shared when it's your turn. And so with that, I would kick off with, so I would stop sharing my screen. Yeah. And the first person would be June Q. I'm sorry if I didn't pronounce it well, but yeah, the first presenter. And please, you have to have your camera turned on while sharing your screen as you present your poster. Thank you.
Hello, everyone. Can everybody hear me clearly? Okay. Hello, my name is Jun He, and now I'm going to share my screen. So can you see my screen clear? Okay, I'm going to start. Good afternoon, everyone. My name is Junhe Cui. I'm a PhD student from Columbia University. I'm working with Professor Jacob Fish. Today, I'm going to share our proposed unified thermodynamically consistent multiphysics model for simulating the overmolded thermoplastic interfaces. The key message of this work is very simple. With our multiphysics model, we can predict both the manufacturing-induced damage and the final product's mechanical performance. In other words, manufacturing history is not just a processing detail. It determines whether the final product performs the way we want it to. So let's now start with the motivation. What is overmolding? Overmolding is a manufacturing process where hot polymer melt is injected onto an existing substrate and then cooled down to form a single integrated component. It's attractive for lightweight composite manufacturing because it offers an efficient way to make high-performance structures, such as automotive panels and aerospace interior parts. But the key issue is the interface, because the final product's performance depends strongly on the quality of the interface. However, it is very hard to predict the interface. Several physical mechanisms happen at the same time. Polymer diffusion across the interface helps the bonding. However, the polymer crystallization reduces chain mobility and it makes it harder to bond. At the same time, the part shrinkage, together with mold constraint, will generate significant residual stress, damage, or even delamination. So even if a final product looks fine geometrically, its interface may be already weak or even damaged, during the manufacturing. That's why this problem matters. And that's why the industry still relies so much on the trial and error. And what's new in our research is that instead of treating the heat transfer, bonding formation, and part shrinkage as separate processes, we connect them with a unified and thermodynamically consistent framework across multiple domains: the bulk material, the nanoscale interface, and the zero thickness interface. It is thermodynamically consistent because all the equations satisfy the first and second laws of thermodynamics. It is unified because the zero thickness interface formulation is derived from the nanoscale interface formulation. So in this way, the physics stays connected across scales. And the main idea of this model is very simple. Temperature is the primary driver. In the cooling process, temperature governs the polymer diffusion, the crystallization, and part shrinkage, which together controls the final product, which controls the quality of the bonding at the interface. In the bulk material, we track the cooling and part deformation, and in the interface, we track the formation of the bonding. All this information will then be used to predict the strength and potential damage at the interface. The main message is that the manufacturing history shapes the interface states, and the interface states controls the final product's performance. And finally, to show the model is accurate, we first verify it with this ECA specimen. Since the temperature is the primary driver, we first verify our predicted temperature field with the mold flow solution. And then we compare our predicted interface damage with the experimentally observed interface macrocracks. And our predicted ash concentrated interface damage agrees with the experiment. Now we can see our model is able to capture the manufacturing-induced damage given the processing conditions. And to further validate the model, we use this shear lab specimen, which is designed to test the final product's mechanical performance. A tensile shear test is performed on the specimen, and we compare three sets of force displacement curves: the experiment, the simulation with manufacturing history, and the simulation without manufacturing history. And from this plot, we can see only the result with manufacturing history agrees with the experiment. The simulation without the manufacturing history significantly overestimates the response, which is completely unacceptable. So from this result, we can see that an accurate final product performance requires the manufacturing history. So to conclude, in this work, we proposed a predictive framework that links manufacturing, interface evolution, damage, and final products performance. The key take-home message is that if we want to predict a real interface integrity and real final products performance, we need the manufacturing history. Thank you. Thank you. That's it. Any questions or comments?
Thank you. Does anyone have questions?
Yeah, hi. I have a question. That was a very nice presentation. So the question that I had was like in your crystallization equation, it looks very similar to Avrami equation.
Yeah.
So I'd like to know like if the parameters are like dependent on cooling rates or
Yeah.
yeah, is it assumed to be some kind of a constant?
No, it's not a constant. It depends on the instantaneously changed cooling rate from the simulation. So it's a
Oh,
highly nonlinear model.
okay, thank you.
Thank you.
Any other question? Um, um, okay. In the absence of no further question, thank you very much for your presentation, June. And the next person would be Tu Wayne.
Can everybody hear me?
Yeah, we can hear you.
Okay, now I'm share my slides. Okay. All right. Good afternoon, everyone. My name is Wayne Chu. I'm a PhD candidate at the University of Michigan. My advisor is Professor Abkin Filipov. So I'm presenting our research on how we use the mechanics of basket weaving to design and fabricate 3D functional metamaterials. So as we all know, basket weaving is this efficient strategy to convert one-dimensional materials to three-dimensional structures. Now, this benefit in geometry is a strong motive for people to weave baskets. But here we want to ask, are there any mechanical benefits for weaving these baskets? So to answer that question, we first look at the geometry of a woven basket. And through our study, we found out the two-dimensional woven patches in a basket are connected by this local three-dimensional which is what we call a woven corner. So this corner structure I'm holding here is the reason why 2D patches can be assembled into a 3D structure. And by further study of this woven corner structure, we found out compared to continuous corners, woven corners can provide similar stiffness, much higher resilience when it comes to large deformations, which means this woven corner here can stand extreme compressions, and after remove this load, it can perfectly bounce back and recover the initial geometry. And we can do this type of, extreme deformations again and again without causing permanent, significant deformation. And because of these two amazing properties on the high stiffness and high resilience, next, we're going to use these woven corners as our fundamental Lego units to modularly assemble woven systems that have more complex geometries and functionalities. So here we showcase two examples. In our first example, we have these woven robotic structures that are soft for safe human-robot interaction, so stiff enough to carry those heavy loads to achieve this load bearing functionality. We also showcase examples of how we use these 3D woven surfaces to make personalized exoskeleton surfaces that can adapt geometry of our different human bodies of different individuals. On top of that, these 3D woven structures, they also have applications in automotive parts, architecture, and consumer electronics. All of these systems, they require high stiffness and high resilience at the same time. Thank you. I'll be happy to take any questions.
Any questions?
Yeah, hi. I have one question.
Yeah,
So
please.
yeah, it was very interesting to see. So the question that I had was like in the context of like woven composites, you have like many
Mhm.
different possibilities in terms of like the size of or the thickness of whatever is being woven. So I think the search space would be like really a lot to identify what is the best possible combination to get a particular property.
Hmm.
So like, do you use any like efficient search techniques, or is it more like a trial and error kind of a method?
Oh, yeah. Thank you for your question. That's a great question. So, the methodology we are using in our study, when we study the mechanics of the structure, they have two parts: experimental testing and simulations. For testing, we use the universal testing machine to test to get these low displacement curves. And also we also use this 3D scanning techniques to scan the surfaces to validate whether our simulation can replicate the geometry of a physical prototype. So that's on the experimental side. On simulation side, we developed this reduced order mechanics model. So it's basically an FEM model, like a finite element model, but here we are using only two types of elements. We call it bar and hinge model, because we only use hinge elements and bar elements so that the simulation can be very efficient, but also maintain that accuracy. And we did our own, programming in MATLAB. So this is our own reduced order simulation package. Thank you.
Okay,
I
thank
have
you.
a question as well.
Yeah,
Great,
please.
great presentation. So one question I have is, what material do you use here, and does the material really matter when you consider the overall stiffness of the structure?
Hmm. Thank you so much. So here, the prototypes you are seeing, they are mostly made of mylar, which is a type of durable polymer materials. But besides mylar, we also used, very thin wood sheets and very thin steel sheets. So regarding stiffness and resilience, the materials do matter. I mean, the specific quantities, they will vary when we change the material. But this high stiffness compared to continuous counterparts, and also this resilience under cyclic extreme deformations, these two qualitative properties, they will remain even they will maintain even when we change our materials. So yeah, thank you.
Thank you.
I have one question.
Yeah, please.
So how does the performance of your woven metamaterial scale when fabricated, like at the micro or nano scale? Like, do you anticipate the
uh
same stiffness or
Sorry,
resilience?
I think I'm oh sorry, I think I don't know if it could be my internet, but like it kind of like
Oh, okay,
yeah,
sorry.
so I didn't hear the questions. I'm so sorry. Yeah.
So my question was, how
Hmm.
does the performance of your woven metal materials scale, like when you have them
Hmm.
fabricated at micro or nano scale, like do you anticipate the same stiffness, resilience, or is there a trade-off in terms of like the length of scales you'll be looking at?
That's a ve Thank you so much. That's a very good question. So we're actually currently working on that. We have these collaborators who have expertise in micro nano fabrication, and we are trying to extend this methodology to fabricate those, woven micro or even nano devices. And right now, the results I'm not showing here, but right now we're observing very similar phenomenon. So compared to continuous devices, they still have that high stiffness, but in the meantime, they have amazing resilience when it comes to large deformation. So yeah, I'm gonna say these properties, they are very robust regarding scales. Thank you.
Thank you.
Thank you so much.
Thank you for your presentation. The next person would be Takwe. Yeah.
Hi, yes. Am I audible?
Yes. And you're able
Yeah,
to share your screen. Yeah.
sure. Is my screen visible?
Yes.
Just a moment. Sure. So, I am Tawqir Nasir. I work with Professor Somnath Ghosh. I'm going to talk about machine learning enabled parametrically upscaled constitutive models for fatigue crack nucleation in titanium alloys. The motivation for this research comes from the fact that dwell fatigue is the cause of failure of critical aircraft engine components like these disks. And microstructure plays a key role in the dwell fatigue life of these components. Here we can see microtextured regions in these EBST scans that impact the fatigue crack nucleation or in general fatigue life of these components. This brings us to the key question. Is it possible to have a continuum scale model that can model the microstructure based response and crack nucleation in component scale? So conventional methods of multi-scaling are computationally intensive and computationally expensive, and they render the problem computationally due to the computational expensiveness, they render the problem intractable. So we propose a solution based on parametric upscaling. So what are these parametric upscaled constituent crack nucleation models? These have three modules. The first one is experimental data, where we get the experimental data and then do the mechanical testing. We use this data in our second module, where we develop the crystal plasticity based micromechanical models for grain scale crack nucleation prediction. And then we generate the database from using these micromechanical models and develop the upscaled models that have the dependence on the underlying microstructure. Now, as we can see from here, these are the equations that represent the model. As we can see, the material response is a function of the underlying microstructure. Here you can see the elasticity tensor is a function of the underlying crystallographic texture. Similarly, plastic response is a function of the grain size and misorientation. In addition to this, we have a crack nucleation probabilistic framework for crack nucleation prediction, which is again a function of the underlying microstructure. So applying this model to a notch specimen to explore the effects of the microstructure and geometry, we take a double-edged notch specimen where we have two different types of notch. One is a shallow notch, another is a deep notch. And we assign two different microstructures for which we assume the signature as microtexture intensity. Here we see in general the cycles to crack nucleation with increasing load come down. But we can see the effect of geometry as well as the microstructure. We can see that the shallow notch has higher crack nucleation life. Also, we can see when the MTR intensity is higher, the crack nucleation life comes down. Whereas this variance comes down, this shrinks as the load increases. So that means as the load increases, the microstructure effects go away. Next, we apply this model to the actual component. We have a disk where we take the axisymmetric part and then apply two types of microstructures. In one case, we apply the uniform microstructure. In another case, we apply different microstructures to different zones of the disk. And then we apply the centrifugal loads, and then we see the crack nucleation life as a function of the increasing applied load in terms of RPM in general comes down. Whereas when we take different combinations of these microstructures or different permutations, we see at lower loads, the sensitivity to microstructure is much higher. And as we increase the load, the sensitivity to microstructure comes down. In addition, we also observe that when when the underlying microstructure changes, the crack nucleation life in certain cases rises from 33,000 cycles to 53,000 cycles. And also, we can notice that in one case, the crack nucleates at a different location. So the ultimate objective was to validate this model. Then with experiments, we have some experimental results where we know the underlying microstructure from EBSD scans. We quantify that, and then we assign that microstructure to our parametrically upscaled model, and we try to compare our predictions, fatigue crack nucleation predictions, as a function of the MTR intensity. In general, we see a continuous decrease in life as a function of the MTR intensity. We can see that our PUCNM predictions match the experiments well, whereas we also try to do the same type of modeling, crack nucleation prediction, using a J2-based FIB model, which has no information of microstructure. So that is where the J2 lacks and PUCNM performs well. So once this model is calibrated well, it can be also used for prediction of crack nucleation life in the actual components, along with the uncertainty in life. So yeah, that's it from me. Thank you.
Thank you for your presentation. Do we have questions? Okay. I have just one question. You mentioned
Sure.
about the deep notch geometry, how it suppresses like the effect of the microstructure on fatigue light.
Right.
So like
Right.
the PUCM framework, like how can it be integrated into like certification workflow for aircraft engine
So
components, and like how does this affect like the microstructural characterization required by manufacturers?
So this framework is actually designed for qualification and certification projects. So as you can see here, that because the continuum scale model is able to take the underlying microstructure into account, so we can so this model has been can be provided to the users in the form of, let's say, in the form of UMATs, and they can do the part analysis using a commercial finite element analysis software. And on top of that, this can also be used for design. Let's say if we do some inverse mapping using optimization algorithms to optimize which microstructure gives us the perfect crack nucleation life that is required.
Okay. Thank you.
Thank you.
So thank you for your
I'll
presentation.
I'll just stop sharing.
Yeah. The next person would be Nick Ravito.
Hi. Let's see. Okay, can everybody hear me okay? Perfect. Okay, hi everyone. Thanks for having me. My name is Nick Ravito. I'm going to be presenting on the network effects in thrombolytic therapy for stroke. Stroke is a leading cause of death and disability worldwide, which occurs when an artery in the brain is blocked by a pathological blood clot called a thrombus. One of the leading treatments for acute ischemic stroke is intravenous thrombolysis, which involves administering a clot-dissolving agent called TPA. Despite IVT's widespread use, we see successful recanalization in as few as 30% of cases. And one hypothesis for these failures is that a blood clot in the vascular network forces drug away from the clot. Computational methods are uniquely well suited to study this phenomena, as we can directly measure fluid and drug transport, construct arterial geometries from medical images, and easily parameterize experimental setups. In our case, we construct the heart-to-brain arterial structure from patient-specific CT images and extract the circle of Willis, the brain's major blood distributor. We model stroke-inducing clots in each outgoing circle of Willis artery as a fully occlusive spherical domain, which you can see in the center panel of box 2. We can run, or we do run 3 cardiac cycles while modeling fluid dynamics using the stabilized fictitious domain finite element method for the Navier-Stokes and the Brickman penalized Navier-Stokes equations with realistic clot permeabilities in the stroke cases. Then we can use the resulting flow field to run 10 cardiac cycles of drug transport. We use physiologically realistic inflow conditions based on the patient-specific cardiac output, prior heart-to-brain CFD models, and a physiological inflow profile, as shown in the left panel in box 3. Time average pressure outflow conditions are also informed by prior work. And in the right panel of box 3, you can see how the presence of a clot forces flow away from the artery with a stroke. In this case, it's the RACA, or the right anterior cerebral artery. Next, I want to discuss the stabilized fictitious domain finite element method we use to model drug transport in the brain. This is box 4. The diffusivity of TPA and the thrombolytic agent is realistic. And additionally, we model a hindered diffusivity in the clot by imposing an order of magnitude decrease in diffusivity. Diffusivities at the scale make the system's Peckley number very large, like on the order of 1 times 10 to the 6 or 1 times 10 to the 7. And as a result, the ADR system is nearly hyperbolic, and the standard stabilized advective form of the advection diffusion reaction equations oscillates unrealistically. So to combat this, we use the skew symmetric form of the ADR equations, which has half of the advective form and half of the conservative form. This formulation conserves the L2 energy norm and prevents that oscillation that we saw unrealistic from the standard form. And in this figure, you can see how TPA is forced away from the clot region again in that RACA stroke case. Moving on to box 5, we can see that the time integrated outflow flux varies dramatically across all the stroke locations, which is the left panel. And the contralateral outlets account for more of the drug outflow than the outlets ipsilateral to the stroke. This is a result of the proximal collaterals, which are the left and right communicating arteries, the posterior communicating arteries, and the anterior communicating artery. The center and rightmost panels show the changes in drug flux through these collaterals in the RACA stroke case. And we can see that more drug passes through the ACOA, and so the anterior communicating artery and the posterior communicating arteries in stroke, and the RAC stroke, and less to the left and right communicating arteries. So to conclude, we've shown that while proximal collaterals may promote perfusion in stroke, they also introduce non-intuitive transport that significantly alters drug transport during stroke, potentially reducing the amount of drug that reaches the clot and potentially reducing the lysis rates, so the clot dissolving rates. We've done all of this using a tailored numerical method for patient-specific drug delivery and patient-specific drug transport problems. I also want to briefly acknowledge the CU Alpine High Performance Computing Center and also the National Science Foundation for funding this work. Thank you, and I'll open up for questions.
I have
I have one question for you. Oh,
Go ahead, please.
Sounds good.
okay. So, how many vessels you modeled in the brain?
I'm sorry, could you say that again?
How many vessels you modeled in the brain? So, blood vessels or
I'm not sure, like how many methods? Is that what you're asking? I'm sorry.
no blood vessels? So, how many bifurcations you have? How many vessels?
Okay, yeah. So our computational geometry is shown in this center panel of 2. So it is only this, right now we're only using this one patient, but it has 3 inflow and then 6 outflow vessels. And then we model, as continuing work, we're also modeling anatomical variations where the communicating arteries may be removed. But it is
Okay.
just this one panel. This is our computational domain.
Okay, thank you.
Yeah, thank you.
I have a question.
Yeah.
Can you expect the same behavior or effect for any size of the clot or permeability, or does it reduce as you increase the permeability?
Yeah, so as the permeability increases, we would expect more flux through the clot that's occluding the stroke or occluding the vessel. We do have some models that model that lysis rate. So as blood brings drug to the clot actually dissolves and becomes more permeable. That's pretty computationally expensive, so we chose to not use that here. And it's also on a very long time scale. These treatments are over an hour, and we're modeling roughly 10 seconds.
I see. Thank you.
Yeah, thank you.
Any more questions? I guess. Okay. Thank you very much for your presentation.
All right, thank you.
The next person to present will be Jessica Holmes.
Hi, everyone. Let me share my screen really quick. Okay, can you see that all right? Okay, cool. Okay, so my name is Jessica Holmes, and my poster is titled A Particle Continuum Method for Investigating Clot Flow Interactions. And so I conducted this research alongside Nick Ravito, whose name might sound a little bit familiar, and Dr. Devanjan Mukherjee at the University of Colorado Boulder. So our work addresses ischemic stroke, which it represents a major cause of death and long-term disability worldwide. And stroke stems from blood flow disruption by a fragmented blood clot. And we've seen that clot composition and local blood flow heavily influences treatment outcomes for stroke. However, current imaging techniques can't resolve these complex interactions between the blood flow and the clot microstructure at the scale we need to characterize how the flow mediates treatment efficacy and disease progression. So to bridge this gap, we've developed a customized fictitious domain numerical framework where we started by creating a discretized flow domain from image-based patient-specific vascular, and that's seen in box 2. And then to replicate the physiological conditions, we prescribed a pulsatile flow velocity with a parabolic inlet condition to the geometry. And then we solved the incompressible Navier-Stokes equations using the stabilized finite element method paired with the fictitious domain method to resolve the flow through the clot domain that we constructed using discrete particles. So you can see the specific FEM weak form that is driving our model in box 2 as well. For our numerical experiments, we systematically varied porosity and average particle size to create distinct clot permeabilities, which we then compared against scenarios with no clot, an impermeable clot, and a homogenized porous clot. And so an example of the reconstructed clot microstructures with a medium average particle size and varying porosity are seen in box 3. So let's go over some results. So a major strength of our methodology is how it resolves multi-scale flow features. So in a single simulation, we resolve macro-scale flow and local advective transport, permeation to the clot interior, and subsequent micro-scale flow and diffusive properties. So we observed that the arterial curvature yields pronounced helicity within the flow. And furthermore, the local bifurcations induce shunting to the proximal branches in front of the clot, which reduces the flow-induced loading on the clot boundary. We also saw local recirculation and back-propagating swirling structures from that form as the bulk flow is rerouted towards the nearest adjacent branches. You can see this in box 4. So we believe that this observed flow shunting might also alter the permeation pressure gradients that are needed for biochemical transport to the interior of the clot. And because of this rerouting, the occluded branch experiences flow rate reductions of several orders of magnitude distal to the blockage, which we would expect. But the occlusion's presence decreases the overall outlet flow rate by at least 85%. So there's a big jump even when the porosity is pretty high. So to measure the extent of the permeation to the clot interior, we calculated the radial pressure gradients around the clot surface, and these are seen in box 6. We found that permeation moves inwards at the proximal boundary of the clot and then shifts outwards distal to the boundary. We observed very minimal changes in pressure gradient magnitude as we shifted the porosity, but we did see a strong increase in heterogeneity in the pressure gradient field that correlates directly with average particle size. So in conclusion, our methodology captures local flow in the clot environment within the branching and curvature of the arterial domain, coupled with variations in clot microstructure. And we've demonstrated that pressure-driven advection is important for initializing intraclot transport and can be influenced by local flow redistribution and those recirculating structures that we saw. So I wanted to thank the University of Colorado Boulder Research Computing Group as well, and thank you for the opportunity to share my work, and I hope you enjoy. I'll take any questions.
I have one question. How sensitive, are the permeation pressure gradients to the variation in the clot composition?
Yeah, so we see that the permeation pressure gradients, when varying porosity, actually have very similar magnitudes. But when you vary the average particle size, so let's say there's really large groupings versus small groupings, there's a much more heterogeneity in the pressure gradient field. So meaning that there's these very specific transport pathways that are correlated with large particle sizes that allow for the advective transport to kind of enter the clot a little bit easier, enter and exit the clot a little bit easier. So there's definitely some correlation between both, but I would say that we see a lot stronger of a correlation with that average particle size.
Okay, thank you.
Yeah.
I have one question.
Yeah, go ahead.
So I just wanted to know, how do you make sure that the stabilization technique does not affect the accuracy of the results, or maybe you're not interpreting the results in some other way?
Yeah, the stabilization is really there. I mean, it's a canonical formulation, so we have verification that it's giving us an accurate representation of the system. When we look at the mass balance error rates of our simulations, they're about 1%. So we expect that it's pretty accurate to at least some extent. Of course, that stabilization is there because any stiffness within the system is probably going to cause the system not to be very numerically stable. And so we have to have those stabilization terms in the weak form so that we can even really run the simulations to begin with. So they're canonical formulations, and I think that they're well integrated within a lot of multiphysics, like multi-scale solvers that make them pretty robust.
Okay, thank you.
Yeah.
Thank you very much for your presentation. And the next person we'll have is Wang Luchang.
Hi, yeah, it's me. So let me share my screen. Okay, yes. So yeah, I'm Luo Chang from the University of Pittsburgh, working with Professor Jihan Liu. And this poster is about the osmocapillary surfaces with the swollen solids, where the osmotic pressure, surface tension, and elasticity interacts to show some rich physics. The key phenomenon here is the phase separation at the surface. Imagine a swollen solid, such as a jelly, hydrogel, and tofu. They can locally exude solvent outside from the surface and creating a small solvent region that is called the phase separation. And this locally separated solvent region can change surface shape and can modify the contact line geometry and can also evolve with time. And our goal is to build one computational modeling framework that predicts how deformation changes the surface topography and what geometry forms at the contact line, and also how the phase separation zone grows over time. And in part one, we predict the gel surface topography under stretch. In our computational model, we do not model real phase. We model only the surface. The substrate is a Neo-Hookean solid. The surfaces are modeled as beam elements with surface tension inside. And osmotic pressure is modeled as a line pressure. And we apply frictionless sliding, no penetration as our contact. We find that in plane strain case, phase separation reduces with stretch and the surface becomes rougher. This means the solvent actually gets absorbed inside the gel's bulk. And the phase separation can disappear under large stretch. When we compress the gel, the solvent can be squeezed out and submerge the surface. And we have a phase diagram here to predict whether the surface is dry or wet under different loading conditions. The same phenomenon also found in the experiments. And in part two, we focus on wetting at the droplet contact line. When a droplet sits on a swollen gel, the solvent can exude near the contact line and form a phase separation, which creates a four-phase contact zone. The objective for this part is to predict the geometry of that zone. We use a similar finite element setup, only model the surface as well. And this time we lift the contact point up. And the equilibrium state is how the contact zone looks like. We find that the higher osmotic pressure suppresses phase separation, and a stiffer gel promotes phase separation. The phase separation size and the solid deformation scale is governed by an osmocapillary length and a elastocapillary length, respectively. Our result agrees well with the experiment data from the other literature. In part three, we predict the dynamic growth of the phase separation. We model the gel as a semi-infinite poroelastic medium. Near the contact line, the surface separation zone is modeled as a capillary-driven boundary condition. And we solve the poroelastic transportation in the bulk to obtain the solvent flux at the boundary. And we then map this, we then use this global mass conservation to convert this flux into the growth of the separated solvent volume. And we then map the volume back to the change of this this phase separation width. We update the active boundary region with a moving boundary approach. And this model predicts that the phase separation width actually grows as a power law, and the surface height behaves non-monotonic. This result shows strong agreement between simulations and experimental measurements from the other literatures. So to wrap up, phase separation is the key phenomenon that links surface topography, contact line geometry, and the transportation dynamics on swollen solid surfaces. This computational modeling framework provides potential ability to tune the surface shape, tune the wetting behavior of the surface, and also the kinetics of the surface. And that's all from my presentation. Thanks for your time. Any questions? Thank you.
No question. I have a question. You show that like the phase separation follows like a growth order, like a power law order. Like what physical mechanism would limit this growth rate and like to a specific exponent, and how would the dynamics change if like for gels with significantly different permeability?
Actually, in this work, we do not study the nucleation of this phase separation. We start with a finite part of this phase separation and study the growth of this phase separation. So, as we can see in the experimental part, actually at the beginning, this not followed by this 0.32 power law, and at the late case, it's actually agrees very well. So, actually, in the initial part, the solvent kind of exude at this contact line, and as the time goes by, it's kind of saturated because this surface is actually filled with this phase separation. So there's not so much motivation from the bulk towards this surface. So that's saturation. So that's why we have a plateau here. Yeah.
Okay. Thank you very much.
Thank you.
And the next person to present would be Yakuti Mawa.
Yes. Hello, Eric. Can you hear me?
Yes.
Okay, so I'm gonna share my screen, like my. Okay. Designing a new aircraft isn't just hard, it's slow. From concept to first flight, a new airliner can take 10 to 15 years to enter service. Why? Because aerospace manufacturers follow a rigid design pyramid. You start with material samples, then subcomponents, then full-scale prototypes. At every level, you repeat the same cycle. Design, simulate, test, redesign. It's not just time-consuming, it's expensive. One failure near the top can set a program back months or even millions of dollars. This challenge isn't unique to aerospace. It's the same for defense and for automotive and energy industries, demanding performance in extreme conditions. I'm Marwa Yakuti, a PhD candidate in aerospace engineering at CU Boulder, under the supervision of Dr. Mariam Shakiba. My research, supported by the Air Force Office of Scientific Research, tackles a key bottleneck in this process: how to optimize and explore composite designs in a fraction of the time, saving resources and money without compromising safety. Data-driven methods can transform materials modeling, running hundreds of times faster than traditional simulations. But here's the catch. Most AI surrogates are like students who need to see thousands of worked examples before they can solve problems on their own. And in our field, each example comes from a costly simulation. So while solving becomes faster, generating enough training data becomes the real bottleneck. That's where I introduce CompiNet, the Composite Integrated Network. Most existing AI models look at a composite microstructure as if it's just a black and white image. Fiber here, resin there. But in composites, location alone isn't enough. Failure is driven by how fibers interact, their spacing, clustering, and how well they bond to the surrounding materials. CompiNet incorporates physical intuition directly into its design. It represents the composite as a network. Each fiber is represented as a node. and the connections between fibers stored in a connectivity matrix capture how they relate to each other, like fibers' nearest neighbor distances. These connections show how stress can travel from one fiber to another. Compinit looks at the problem through two complementary lenses. The graph neural network captures the big picture, understanding the overall material behavior by considering the position and interaction of fibers. At the same time, the convolutional neural network focuses on the fine details, tracking how stress moves at the pixel level. Given a composite microstructure and loading condition, Compinit predicts the full stress distribution across the material. In our results, we show that Compinit accurately reconstructs full field stress maps, reduces the amount of required training data by 20 times, and achieves up to 150 times speed up compared to traditional finite element simulations. The result is a model that delivers full field stress maps in seconds, giving designers instant visibility into stress hotspots and likely failure zones. That means they can screen millions of layouts overnight and move only the most promising designs to costly experimental testing. The real power of Compinit isn't just making simulations faster, it changes what's possible for engineering. Compinit has applications across multiple domains. In aerospace, it enables real-time structural health monitoring, moving from scheduled inspections to active digital twins. In 3D printing, it allows defect detection, preventing failures before they happen. And for design optimization, it dramatically accelerates R&D, letting engineers explore millions of designs instead of relying on a single expensive simulation. Currently, I'm working to take Compinit from the lab to real-world deployment. I'm seeking collaborators who can provide experimental data, partners interested in integrating this into their design workflows, and support to expand it to 3D microstructures and large-scale applications. By removing the computational bottleneck, we move from slow, sequential testing to truly rapid design exploration. Thank you.
Hi, Mava.
Hi.
Hi, great presentation. Thank you.
Thank
So
you.
I have a quick question. Maybe you already talked about this, but can you tell us a little bit more on the motivation for you to integrate, convolutional and graph neural networks? Thank you.
So yeah, the idea of like integrating the graph started from, it started from like the similarity between like a graph network and the composite microstructure. So in our graph network, so each node represents a fiber, and the edges captures information on like nearest neighbor distance, like the distance between the fibers. So we saw first that most existed like. So yeah, I mean, existed like data-driven methods use like convolutional neural network and like use thousands of samples during training. And they mostly use the black and white picture representation of the microstructure. So yeah, so this is where the idea came to incorporate like the graph as an attempt to reduce the size of the required training data. And it worked. Like now we need like 20 times less training data compared to existing models.
I just have one question. How well does your model generalize to a different composition of fiber, like different fiber composition of volume, like that is outside like the training data?
So yeah, so the composite like the model can generate like we have like within, so like we trained the model on 40%, on 55% fiber volume fraction, and we did test it on 40% and on 25%. So we saw that like the model, like the accuracy did like decrease a bit, like it's not like as the same performance as like the training data, but we still get like good results within that range of fiber volume fractions.
Okay. Thank you. Any other questions? Okay. With no further questions, thank you for your presentation.
Thank you.
The next person that we're presenting is Olivia Ward.
Hello. Let me go ahead and share my screen. Okay. Lovely. Can you all see my screen?
Yes.
Okay. Sorry, 1 second. Okay. Hello, my name is Olivia Ward, and today I will be presenting my work on the analysis of indentation penetration problems in soft solids. This work was conducted at the Georgia Institute of Technology in collaboration with Deep Malu, Professor Yu Hong Hu, and Professor Aditya Kumar. Indentation and penetration of soft materials are important in many real-world applications, including medical procedures, understanding animal bites, and designing puncture-resistant materials. However, measuring fracture properties in these materials is particularly challenging. So traditional fracture tests, such as pure shear or trouser tear tests, often fail for very soft materials like hydrogels, and this is because these materials undergo large deformations and significant energy dissipation, which makes it difficult to isolate the true fracture toughness of the material. So indentation penetration, or IP testing, is an alternative approach that has been used for elastomers. This test is local and provides a more accurate prediction for the fracture toughness because there's no need to account for viscoelastic dissipation in the material. However, it does not directly translate well to ultra-soft materials where unstable crack growth and inconsistent results are common. So an example of this can be seen in Figure 2, where there's a very large deformation in the hydrogel before fracture. So the key question we want to address with this work is how can we modify indentation penetration tests to reliably measure fracture properties in soft solids? To solve this, we introduce a pre-notch into the material before performing the penetration test. So the idea is that the notch will act as a stress concentrator, and instead of cracks forming unpredictably, the notch localizes where the crack begins and promotes stable crack growth during penetration. You can see this concept illustrated in Figure 4, where we show the geometry of the indentation penetration setup, along with experimental images of controlled crack propagation. Next, we use a Griffith energy balance framework to analyze the system. So in simple terms, fracture occurs when the energy available from deformation is sufficient to create new crack surfaces. So using this idea, we can predict the size of the crack and relate it to measurable quantities like force and displacement. We also used a finite element model in Abacus, and this is shown in Figure 5. So the complex geometry of the indenture tip requires us to use FEM. And we use this, to calculate the strain energy in both the undeformed and deformed configurations. So this allows us to quantitatively predict crack growth under different conditions. So now I'll go ahead and highlight our key results. So first, we developed a new experimental model for notched indentation penetration tests in soft solids. So in Figure 6, you can see force displacement curves for these tests. And unlike traditional methods, the curves show stable and repeatable behavior, which is critical for reliable measurements. Second, we discovered that there's an optimal range of notch widths that produce stable penetration. So if the notch is too small, the indenter does not have a predefined crack path, and thus the crack will likely become unstable. And if the notch is too large, the system behaves like the unnotched case and will also likely become unstable. So when the notch is sitting in this stable range, the behavior is dominated by the fracture toughness, as shown in Figure 7C. And so this will allow us to extract this property accurately. In Figure 7, we compare experimental data with theoretical predictions, and the experiment between the two is very good, which validates our model. So another important observation is related to crack behavior. So my throat is dry. In very soft materials, cracks can form irregularly, as shown in Figure 3. So, however, with the introduction of a notch, we're able to control crack nucleation and guide it into a more predictable mode 1 opening pattern. This is significant because it allows us to directly connect experimental observations with theoretical fracture mechanics. In conclusion, this work makes 3 main contributions. First, we propose a modified indentation penetration test using a pre-notch to achieve stable crack growth in soft materials. Second, we showed that the optimal notch size can be predicted theoretically and computationally using energy balance principles. And third, we demonstrated that this method can be used to reliably characterize fracture toughness in soft hydrogels. So looking ahead, our future work will focus on developing more advanced numerical methods, including applying the strength-constrained phase field model to this problem. Specifically, we aim to capture the mixed mode fracture behavior that occurs during penetration and to extend our framework to include viscoelastic and poroelastic effects. And these are important, obviously, in hydrogels as well as biological tissues. So overall, our goal is to establish a standardized and reliable method for measuring fracture properties in soft solids, which could have a broad impact across engineering, material science, and biomechanics. Thank you all so much for coming. I'd be happy to take any questions.
I have a question.
Mm-hmm.
Have you conducted this modified test on a non-ultrasoft material to see how the measured properties are different across the modified test and the non-modified test?
Actually, no, we haven't. We've done some stiffer hydrogels to what you see in these results that I'm showing. I'm trying to remember. I want to say the shear modulus was probably around 25, and the stiffness, or excuse me, the toughness was probably around 10. So it's very soft materials still. So no, we haven't conducted this for harder materials.
Okay.
Okay. Thank you very much for your presentation. The next person would be Hikaman John.
Yeah, hi. I'll share my screen. All right, is everybody seeing that all right? I'll take that as a yes. My name is John Hickman. I'm a graduate student at the University of Illinois, and today my presentation is going to center around the embedding of sparse, high-fidelity data into simplified systems to obtain optimized material parameters. The motivation for this work comes from the fact that in existing structures, we know some governing physics, particularly the governing PDEs, but we don't necessarily know exact material parameters or material models. What we also know is that leading data embedding methods can struggle to improve the global effects of the system, and they can lead to ill-conditioned stiffness matrices. We also know that they can be practically challenging to implement and computationally expensive to run, and the predictive capabilities of these methods can lack generality outside of their training data. As such, our contributions are that of the development of a novel multi-scale data embedding technique which enables stable, physically consistent numerical simulations. We do this by embedding the data weakly across interfaces and then leverage an inverse learning procedure to find optimized material parameters. So the general procedure is as follows. We have a target system. You can think of this as a real-life building, and out of that real-life building, we get rich data from a small subsector of that structure. Think of this as displacement through time at one individual node. In this case, we take it from a single element. We then embed that into our surrogate system, which uses a linear elastic approximation to produce the data-driven system. Now, the data-driven system also uses that same linear elastic assumption. However, it uses data from the nonlinear target system to also influence the response. So now we have a displacement field through time, which we can perform an inverse learning technique on to produce this optimal material parameters so that we use the linear elastic assumption, but our parameters more closely match that of the target system. So then the question becomes, how do we actually embed this data into our simulation? This brings us to the data-driven variational method. So I want to restrict your attention to the structure or to the figure up here. We have omega 1, which is the sensor, omega 2, which is the structure surrounding the sensor, and then gamma I, which is the interface that will permit us to transfer data back and forth between these two subdomains. This is shown in the residual formulation on the right. We have our standard body terms associated with the standard Lurkin form shown on the far left and far right. And in the middle, we have our interface contributions driven by the difference in solution at both respective subdomains, omega 1 and omega 2, and the data that we embed. The stabilization tensor then maps this data into a configurational force, which will enforce compatibility between the two subinterfaces towards the data. This is shown in the configurational forces diagram here, where the blue is the interface associated with omega 1, the sensor, the black, the subdomain associated with the interface associated with subdomain 2, the structure, and they're both forced at each point on that interface to match the data. I won't go too much into the actual derivation of the stabilization tensor, but I do want to mention that it has area and stress averaging effects, which allows it to accommodate material and geometric mismatch, meaning that the stabilization is tailored to your specific problem. Given this full displacement field through time from the data-driven system, we can then perform an inverse learning technique to retrieve the optimized material parameters. We start with an initial guess, some candidate material parameters, say from the surrogate system. Then we move forward and forward solve with those material parameters at a specific iteration. When we have those solutions, we compare the displacement against the data-driven system to find an error. If the error is small, we accept those material parameters. If it's not, we take the gradient of that error, iterate to find a new candidate for the material parameters, EI, and continue until convergence. Once we've converged, we select those as our optimized parameters. We put them back into our linear elastic model and produce our optimized linear system. The benefits of this is that we retain the physical insights of the elastodynamics target system, but we have enhanced energy conserving properties, we have the low cost of linear elastic solve, and we actually match closely the benchmarks of typical elastodynamic simulations like natural period and amplitude. Finally, we present numerical results to showcase the efficacy of the method. In the target system on the left, we have a finer mesh that uses a nonlinear neo-Hookean material model, and the material parameters shown below. In the surrogate system, we have a much coarser mesh. We use a simple linear elastic approach, and we give material parameters that are twice as stiff and half as dense. We apply a pulse load and then examine it in free vibration. As we can see above the Morley plots, the target, data-driven, and optimized match nicely, while the surrogate misses in both phase and amplitude. The Morley plots, which can be used to measure frequency of a dynamic system, matches very closely with the target, data-driven, and optimized system, but the surrogate produces frequencies that are about twice as much. Locally, we see that displacement and velocity plots match up very closely for everything but the surrogate, which shows half the amplitude and half the natural period. And on a system-wide approach, we see that the energies are very close for the optimized linear system and the target system, while the data system and surrogate miss. It's worth noting that the data-driven system uses the initial guesses, which were twice as stiff, producing twice the strain energy, half as dense, producing half the kinetic energy, which only further emphasizes the need for the optimized material parameter approach. And then finally, we show the phase diagram where the optimized linear system, the data-driven system, and the target system match nicely while the surrogate system misses. I appreciate everybody's attention, and I'd be happy to answer any questions now.
Hi, John. Nice presentation. I have one question.
Mhm.
So, how transferable is the model in case you change maybe the shape of the domain or something like that? Given that it's a dynamic situation, do you expect like wave reflections to change the applicability of the model?
Is the question, so would the surrogate model change?
Yeah.
Okay, but the target system would stay the same?
Mm-hmm.
Well, so the data is taken directly from the target system. So if we were to embed that data into some different geometry, you would get a different response, of course, because those eigenvectors are based off of the actual bounded domain that we analyze. With that being said, as long as you match that outer domain, when it comes to the discretization and the selection of elements, those all match very nicely. But you wouldn't want to change the actual geometry. The actual boundaries should stay the same between all the models. Outside of that, there's a lot of flexibility.
Okay, thank you.
Mhm.
I have one question. How does larger deformations or like more complex loading affect the accuracy of the surrogate model?
Yeah, it's a great question. So that's actually what we looked at specifically in this paper, was extending these deformations to the exceedingly nonlinear regime. We can see that the displacements at node B here are around 5, and at A, they're even higher. So the question, yeah, does it affect accuracy? In the linear elastic regime, we're able to modify boundary conditions and give much larger spreads by using the same model, but in this case, we use a linear elastic model. And so that large deformation is compensated against the linear elastic model to match that of the Neo-Hookean through this embedded data. So there is significant changes when we increase the size of the displacements, but that is accommodated through this DDV approach.
Okay. Thank you very much. Any other questions? Okay. And the next person that will be presenting is Prata Lucas.
Hello. Can everybody hear me clearly?
Yes.
Okay, I will share my screen now. All right. Hello, everyone. My name is Lucas. I am a PhD student here at Johns Hopkins University, and I'm going to talk a little bit on the work I've developed here on an approach for fatigue crack growth modeling on LPBF Ti64 that considers the microstructural characteristics and the defect structure. So let's start with why we're doing this. In components and structural parts that demand high performance and are subject to fatigue loading and fail by fatigue loading, we know that about 80% of the part life is encompassed within the regime of short crack growth and crack nucleation. The long crack growth takes only the remaining time of the part life. However, whenever we model fatigue, so we estimate the fatigue life of the materials using Paris law or some other model, these are just empirical equations that don't take into account the microstructural characteristics, which are the driving factors for short crack growth. Since especially in additively manufactured materials like with laser powder bed fusion, that we have high variability of the fatigue life of components. We need to be able to encompass the effects that the microstructure and the manufacturing defects have on the fatigue life of a material. So this is the application of this approach that we're doing here is for Ti64 LPBF, and I'm gonna talk a little bit on how we develop it. The model development is mostly based on images, so EBSD scans to get the microstructural characteristics and micro CT scans for the defects. So specifically, Ti64 has this very complex microstructure of called the Widmanstätten microstructure, in which we have these needle-like lats that are very cumbersome. We have different variants of the crystals due to the recrystallization of the material. It's an HCP crystal, so it's highly anisotropic, and we need to take all of that in account when developing our model. So what we do is that we characterize this microstructure in terms of distributions so that will describe this microstructure as through parameters. For instance, a distribution of grain size, volume fractions of the different HCP variants, so the different crystallographic orientations of the crystals, and the correlation between the variance and the positioning of the defects to the microstructural grains. Now, these alpha lats, they are very, very fine and very small. So if we were to model a large volume of it, it would be pretty much computationally unfeasible, because imagine just discretizing this. So we want to embed in an effective crystal plasticity model these parameters that describe the microstructure such that we don't have to explicitly represent the grains. So for that, to develop this model, we create a set of realizations of the joint distribution of these characteristics in which we explicitly represent the lats. We simulate these synthetic microstructures with regular crystal plasticity, And then we perform sensitivity analysis and use machine learning to figure out which of these microstructural characteristics affect which of the overall microscopic, not microscopic, but overall behavior of the material at this level. And then with genetic programming based symbolic regression, we come up with explicit expressions of these parameters. So such that we now can represent the microstructure in a formulation, in a crystal plasticity formulation, without explicitly representing the morphology of the grains. On the other level, when we get a sort of lower resolution of the EBSD scans, or like in a much broader field, and we reconstruct the parent beta grains that gave rise to those laths, we can see the directionality that is natural to the manufacturing process. So we must be able to capture also these characteristics. So we extracted the the distributions that describe this beta level grains, and we reconstruct using Dream 3D these statistically equivalent representative volume elements that then we are able to run using our effective crystal plasticity model. So in these synthetic microstructures, whenever we run the simulations with it, we encompass the distributions of the microstructure in both the alpha level, the very fine lath grains, and the directionality of the manufacturing on the beta grains. But great, that gives us information on the microstructure, but also we need to take into account the defects. So due to the manufacturing process, we have this, we can have a very broad range of defect sizes and shapes. So we decided to approach how to use these defects, to embed these defects in our modeling in two different ways. For very tiny defects, we consider them as a porosity field that is described in the whole domain, and we add an additional parameter f in the crystal plasticity formulation in the Gerson type model, such that we can account for the softening behavior that is expected from and observed from experiments. On the other hand, when the defects that are large and that can be pointy, so they mostly act as stress concentrators, we decide to explicitly embed them in our statistical equivalent RV, such that so that they can actually act as stress concentrators as we know it. So once we have this framework of the microstructure and defects, then we can track the crack propagation. We use the phase field formulation that takes into account the difference in tension compression, the asymmetry, and all the characteristics for elasticity, plasticity, and damage evolution. And we wanted to assess if this phase field formulation would be enough to analyze the competition on driving cracks between the microstructural characteristics are the defects. Because what is normally stated is that, oh, if there's a defect, the crack is going to grow through there. But that doesn't necessarily happen because the environment, the microstructural environment of a defect can be arresting of the cracks. So depending on the microstructure, a certain crack tip might branch out, might be arrested, might propagate in certain directions. And we were able to see that for the same volume, if we have on this path a microstructure that drives the crack growth, but if we add a defect in a region that doesn't have a propense microstructure for crack growth, the crack is not necessarily going to go through there. It's going to go through the microstructure where it's where the energies and the formulation allows for it to grow faster. But this is when we apply a defect at a subgrain level. But now, once we have actual larger defects, we were able to see that, okay, depending on the size of the defect, then the microstructure doesn't have the such effect on the driving path, on the crack path anymore. The crack is gonna go through these large defects because it enhances the stress concentration and all of that. So with this work, we noticed that we were able to capture the competition between microstructure and defect in determining crack path, and this enables us to narrow the gap between using a formulation for fatigue life assessment that takes in account the microstructure, but also is capable of predicting the long crack growth. And with that, I thank you very much for listening to me, and I'll take any questions.
Any questions? Like, I just have one question. Like, what's the variation between like the microstructure driven crack growth and defects for the LPB?
LPBF.
Yes, build. Like, what's the competition between both of them? And like, would it does your model produce like optimal directions for fatigue growth, or like the direction in which the growth occurs?
Yeah, so the trick is that when we model the crack path with phase field, we take into account all of the energies that are would drive the crack. So in some arrangements of the microstructure, those energy levels might be more inducing of crack growth than maybe the surrounding of some defects. So all we cannot, because of that, we cannot say for sure that having a defect is where the crack is going to grow, because the microstructure around the defect might be detrimental for the evolution of these energies. So other regions where we have, uh, like due to the loading and all, we have the higher energetic state for this crack propagation. That's where our model is going to tell where the crack grows.
Okay, with no further questions, thank you very much for your presentation.
All right, thank you.
And then I would share my slide. Okay, so yeah, that brings us to the end of the presentation and the poster competition. I just wanted to like do a recap. We had 10 finalists for this competition that would be judged by our professional faculty judges. Their names are on the screen. So after this, we'll be sending the recording to them for them to judge the different presentations, and they get to pick the first, second, and third place. At the end of this, I would be sharing like a Google form where the audience here get to pick like their favorite poster or their favorite presentation, which is the People's Choice Award. And you're meant to judge based on like the research objectives, the methods, results, the visualization of the poster, and also communication of the presenter. So in the next slide, you see the QR code you could scan to vote for your favorite presentation today. I'll put the link as well in the chat. Mm. And for the winners, we'll communicate the winners via email from after this presentation. Any questions or okay. I think okay, someone has a question. Okay. Oh, thank you. And feel free if you're done like voting, you can leave the Zoom link, the Zoom meeting. So yeah. Thank you for attending. And thank you to the presenters. You all did a great job. And good luck to the winners. 1 second. Thank you. Okay. Thank you. Okay. Okay. Is everyone done? Like, do you need me to share the screen or yeah. Okay. This brings us to the end of the poster competition. Thank you all for attending, and thank you to the presenters as well. You did a great job, and would communicate further details via email to the presenters. With that, I'd like to say thank you and bye-bye, everyone.